We are live. This is Mr. Thomas with a statistical video today. Today we are going to be studying applications of the normal distribution. This is a pretty important lesson when you want to understand statistics. In every statistic class you will come upon this section. And so we're going to start studying this section to give ourselves a good understanding of what does it mean to do applications in the standard normal distribution. I'm going to send out that link so that we can cast a wider audience here today. All right. Let's get the link there. 1 second. And we will begin momentarily. All right. So we're going to get started. So here's where we are. We're in 6.3 today, and we're going to be looking at applications of the normal distribution. So when our data is in a normal distribution and all the assumptions are met, we're now going to be able to do some pretty cool stuff by calculating the probabilities and proportions of certain values in our data set. Let's look at some of the key concepts. So this section presents methods for working with normal distributions that are not standard. That is, the mean is not 0 or the standard deviation is not 1, or both could happen where the mean nor the deviation is 0 or 1. The key concept is that we can use a simple conversion that allows us to standardize any normal distribution so that the same methods of the previous section can be used. And this is one approach. This is the main approach, especially if you're trying to use your table and you don't have technology. If you're just trying to use your table, then yeah, you can take your values, standardize those scores, and then apply table A2. And when we standardize the scores, we mean we convert our raw score into a z-score where 0 is the mean, and also the standard deviation. One standard deviation is exactly 1. That's what we mean by standardizing the scores. Now, here is the conversion formula that allows you to standardize any random x value that you may have. So this conversion factor will take an x value and convert it into a z-score. And what they're saying here is that we normally use z-scores rounded off to 2 decimal places, and this gets it primed for the table. Just think table. If we did not have technology, this was the method, the very traditional method of statistics was always taught, using the tables and charts and converting your raw data values into z-scores. Now, let's look at pictorially what's going on. So we may be given in this section a non-standard normal distribution, meaning it has some mean. The mean could be 100 if we're talking about IQ scores or anything. And the x value could be, say, 122. It could be some random number. What we can do is take the same values, that same normal distribution, because it has the same shape, it's still symmetrical, and convert those values into the standard normal distribution where the mean is 0 and z is the z-score. um, which is basically how many deviations away. That this number is exactly the number of deviations away from the mean. And so now we're going to talk about why we would do this and how would we go about the procedure of this. So here it is. It says the procedure for finding areas with a non-standard normal distribution is number one, sketch a normal curve, label the mean and any specific x values, then shade the region representing the desired probability. For each relevant x value that is a boundary for the shaded region, use the formula 6.2 to convert that value to the equivalent z-score, and then after that you can use your computer software or calculator or table A2 to find the area of the shaded region. This area is the desired probability. Alright, now you're going to see later as I do the problems that you may not have to convert the scores if we're going to be using technology. So we need to really understand why and how we do those kind of things. Let's look at an example. This is actually a really good example. So what we have here, it says Tall Clubs International has a requirement that women must be at least 70 inches tall. Now, here's the context of the problem. Given that women have a normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, find the percentage of women who satisfy that height requirement. Okay, so we really want to know how many women can make it into the tall club. If you have to be 70 inches tall, what is the percentage of women who will satisfy that height requirement? And so what we'll do first is start off with a picture. Let's create a normal distribution. Let's put the mean in the middle, 63.8, and 70 inches is far above the mean, and we want to know the percentage of women who will satisfy that height requirement. So what we really want to know is the area of this pink shaded region. Now, one thing we can do is convert 70 into its z-score, and then we could apply table A2. Okay, but the first step would be to create the picture as we always said. It said given that women have normally distributed heights with a mean of 63.8 and a standard deviation 2.6, find the percentage of women who satisfy the requirement. So we know that the mean, and I may write this down, is actually really good stuff. Let me see if my pen should work this time. Mu is 63.8 and our little sigma is 2.6. Now on the next slide, we're going to convert these values into their z-scores. So let's look at how they do that. It says convert to a z-score and then use table A2 or some technology to find that shaded region. Well, let's do that. If we want to know the z-score, you take that raw score of 70, subtract the mean from it, and then divide by the number of deviations is 2.6. And so this will tell us the z-score of 70. 70 is 2.38 deviations away from the mean. Now we know exactly how far away 2.38 is. Because we took 70, we subtracted 63.8, and then we divided by 2.6. Now the question is, well, how do we actually solve this using our calculator? We know that the z-score is 2.38 and we're going all the way up to infinity, let's actually try to solve this problem. Alright, so what I'm going to do is show you two ways on how to solve this, and this is going to make your life a little easier. So first we'll do second distribute, number 2 normal CDF, and then we're going to put in our lower bound and our upper bound. Normal CDF likes two values, your lower bound and then your upper bound, and it will give you the area that you seek. Now in this case, we don't have an upper bound. We just have a lower bound. So what we're going to do is put in a very large number for the upper bound, and that will be sufficient. That's the way everyone does it. Alright, now normal CDF, we're actually going to use the z-score for the bound, and then eventually we will use the 70, the raw score. So let's do this. I'm going to put in 2.38 comma and then a very large number like 1e to the 99. And there it is. I got 0.00865. That looks like the area that they have identified. But the question is, hey, that's great and all. You didn't put in the mean or the deviation. Well, by default, I use 0 and 1. So let's try this again. What if I did put it in? Which I can. We're going to get the same thing. But now this is the way we normally do it, okay? Now I'm going to show you the way we normally do it in section 6.3. We're going to put in the 70-inch score that we got. So let's just do second distribute, go down to number 2, and then we're going to put in our lower bound is 70. Our upper bound is a very large number. We can make it 1e to the 99. Actually, sometimes people just put in 19, which is a billion. That represents a billion. And then now in this case, we actually have to put in the mean, which is 63.8. And we actually have to put in the standard deviation, which was 2.6. Close it off. So normal CDF can take in 4 parameters: your lower bound, your upper bound, your mean, and your standard deviation. And what you'll get back is the area. And so now we have the answer. In every case, it was the same. Now, why is it slightly different? Well, I actually used 1e to the 9, but at any rate, it's still, this is sufficient. 0.0085485. Even if I think it's also probably, if I did 99, it probably would not have changed much, honestly. Yeah, it would not have changed much. But I think it has something to do with maybe the conversion factor. But these are exactly how you would do it. This is how you would go about doing it in this section. And so now let's come full circle. It says the area to the right of 2.38 is 0.008656. And so about 0.87% of all women meet the requirement. So there, not a lot of women will meet that requirement there. Alright, so let's dig a little deeper and understand this. Number 1, it says, don't confuse z-scores with areas. Z-scores are distances along the horizontal scale, but areas are regions under the curve. And then it also says table A2 lists z-scores in the left column and across the top row, but areas are found in the body of the table. Number 2, choose the correct right and left side of the graph. 3, a z-score must be negative whenever it is located in the left half of the normal distribution. And then 4, we also have areas or probabilities are positive or 0 values, but but they are never negative. And obviously this makes sense to us, right? Area can never have a negative value, and probability ranges exactly from 0 to 1 as well. Okay, so let's take a look at the procedure for finding values from known areas or probabilities. So there might come a time when we may have the area or proportion, and our job is to actually find the x value associated with it. And we know what button we're going to use for that now. So this is going the opposite way. All right, and so let's put this into context. One thing they're saying is, first, sketch the normal distribution curve, enter the given probability and the percentage in the appropriate region, identify the x value being sought out. If using technology, refer to the instructions at the in this section, and also you can use formula 6.2, that z conversion factor, to actually get certain values here. Now, let's do an example of this. So in this problem we have, it says, when designing aircraft cabins, what ceiling height will allow 95% of men to stand without bumping their heads? Men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. First, draw the normal distribution. And so here we have it. We're trying to find that x value that gives us the 95% cumulative probability there, or percentage. And one way to do this now is, notice how we have the mean in the middle and we have the area there. What we're going to use is inverse norm. We don't really have to fool around with all these other conversion factors and stuff like that. Let's try inverse norm and see how far we can get. So let's do that now. Let's pull up our calculator. Let's clear it out. Now you got to keep in mind, from the last section, we saw this happen. When we were given the area, we used inverse norm to get the z-score, but this time we don't want the z-score, we want the x value, the raw value, and so we can do that. Let's do second distribute, and then instead of number 2, normal CDF, we go to inverse norm. Hit enter. Inverse norm wants the area 0.95, comma, the mean 69.5, and then it wants the deviation, which is 2.4, and then close it off. So inverse norm will take in 3 values. If you do not put in the mean or the deviation, then by default it will use 0 and 1. They think you're talking about the standard normal distribution. In our case, these scores are not standardized, so we have to put in the mean and we have to put in the deviation. And hit enter. And what do we get? 63.44, and if we round it off, 8. And that would represent the x value. All right. Now, what did they do? Well, they used the table, and what they've done is dug out the important information. They knew that they wanted 95%, and so in the table they looked up what z-score corresponds to 95%, and they got z to be equal to 1.645 right there, and then after that they plugged those values into the formula to get the x value. This is again without having a calculator, which is not the way to go. You're really going to want to use your technology in this section. That's basically about it, guys. Here's some summary of the procedure on how to proceed through this section. And when you start off, first you need to know, what do you want to find? Are you trying to find area or proportion or probability? Or are you trying to find an x value? And so if you're trying to find the probability, these would be the steps you would take. If you're trying to find the x value, you would go in this direction there. And then you keep proceeding down. They show you the procedure. And these slides are really showing you the steps in terms of using the table without any calculator or technology there, which is a little impractical. On the other side, you could do it, just use inverse norm. Inverse norm, it will be the thing that will help guide you through there. Okay, so that's basically the last of the slides there. Now what we'll do is take a look at some of the problems. If there are no questions, we're just going to keep proceeding on. You can type in the chat. We are live and this video is being recorded. So what we'll do now is just do a bunch of problems, get a feel for the kind of problems that they're asking us. Pulse rates of women are normally distributed with a mean of 77.5 beats per minute and a standard deviation of 11.6 beats per minute. Answer the following questions. Well, we already know the mean is 77.5 and the standard deviation is this. And so we just plug those values in, and they're probably going to want us to find the z-score after that. But first let's plug in these values and see what happens. Oh, what would the scores be after converting them? Oh, so tricky. Well, there's no calculation. After converting them, the scores would be 0 and 1. What are the values of the mean and standard deviation after converting all pulse rates of women to z-scores? Tricky stuff. The original pulse rates are measured with units of beats per minute. What are the units of the corresponding z-scores? It should be the same. Beats per minute. Actually, wait. Z-squared, those beats per minute cancel out, I believe? That's tricky. Let's see. Okay, yeah. The z-scores measures, they actually don't have any units, but we know what they mean. It's the sigma that have the same units. Find the area of the shaded region, and what we have here is, well, this is the graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100, standard deviation 15. And we know that the x value is starting at 115 and everything down, so the lower bound is not there. So what we'll do is pull up our calculator here. Let's pull up our calculator and we'll do this problem. And what we'll do is, let me make this more narrow like that. So we'll do second distribute, normal CDF. Normal CDF will give us the proportion, the area, the cumulative proportion of under the curve. My lower bound is really just going to be a very tiny number, negative a billion. My upper bound is 115. My mean is 100. And my standard deviation is 15. And I got 0.8413. What about finding the area of this between 90 and 120? Same distribution, same mean, and same deviation. So I could just do a second entry, but this time my lower bound is 90. Delete, delete, and my upper bound is 120. Everything else appears to be the same. It's just going to be 0.65629. So I'll round it to 0.6563, I believe. This will be the same type of problem, your lower bound, your upper bound. Let's keep going. Let's see some more problems now. Okay, this is a little different. This time we're given the area and we want to get the x value. And the normal distribution, the context of this problem, we're still dealing with the IQ scores, and IQ scores have a mean of 100 and the standard deviation of IQ scores is 15. So what we can do is, instead of using normal CDF, we can use inverse norm. Second, distribute. Number 3. And for inverse norm, I'm going to put in the area, 0.75, put in my mean, put in my deviation. And it turns out to be 110.1. Now, what if we wanted to actually do this problem using the table? Well, what I'd have to do is find in my table the area that's associated with 75%. So it's not in this one. Let's check the second page. 75%. I'm looking for 75%. So I just have to comb through this table part and find 75%. Now I got the closest thing to 75%. I got 0.7517. That's as close as the table is going to get me, it appears. And so now I got to look up the z-score that corresponds to that. Well, 75%, let's see here. Okay, so 75% is 0.68. 0.68. Remember, 0 is right at 50%. So this is 0.68. And then what I would do is convert that z-score into, I would use my conversion table factor here. Let me see. So we got an area of about 0.75, gave us a z-score of 0.68. And the question is, well, what's the x value that's corresponding to that? Well, what we do know is that that formula is mean, actually, not mean, it's x minus mu equals sigma, which basically means now if I try to solve for x, I multiply both sides. And then add mu over. So z times the sigma plus mu is going to be equal to x. And so now what do? Well, the z is 0.68. Little sigma is 15. And also the mean of IQ scores is 100. And that's all going to be equal to x. And so what I would do after that is just plug this into my calculator. I would do, let's clear everything out, 0.68 times 15 plus 100. And I got 110.2. That is what we got last time. 110, we actually got 110.1. It's because my z-score was really not for 75. It was for a little bit more than 75. But this should still work. Both of them should have still worked. Okay, if I plugged in that other value, I would have gotten the answer right as well. Let's keep going. This is similar, all right? This is a 90%. So we're trying to find what will be the IQ score. What IQ score is in the 90th percentile? That's one way to think of this. The 90th percentile, and so you would do inverse norm there. Inverse norm will give you those values. Okay, so this time, now this is a little tricky because we have the area to the right this time, and inverse norm doesn't give us the area to the right. Inverse norm only works if we have the area to the left. So how are we going to do this problem? Well, what we know is that everything under the curve is 1. And so what we can do, and let me just pull up another sheet here and demonstrate this. Like what they're saying is that this is 85%, this proportion, and we still want to get this x. I know this is a little sloppy, but bear with me. Well, what we know is that, guess what? This is therefore 15%. And so what we can do is say inverse norm of 15%, put in our mean, put in our deviation, and we're good to go. That's going to approximately give us our x, and that would be good. Now, how did we get 15%? Well, 15% came from 100 minus 85, the area to the left of this amount. I wouldn't try to do it any other way. I think I would just stick with that way. Just subtract the area from 1. There's probably some other fancy ways you could probably try to do it, but I just showed you the easiest way. I wouldn't try to make it more complicated than that. It's all pretty straightforward. Let's go back to this last one where it says find the probability p sub 9. This turns out to be which IQ score will separate the bottom 9% from the top 91%. And so P9, in fact, let's describe this on another sheet here. P9, well, what does that mean? This area here, this score is equal to P9. And so what we're trying to say is, what is the 9th percentile? What value, what IQ score separates the bottom 9% from the top 91%? What value would that be? Well, we already know an IQ score is 50 percentile is at 100. So we know x will be less than 100. And if we were to standardize these scores, put the z-scores and standardize the mean to be 0, then we know that this would be negative. But how would we do this? Well, again, inverse norm, because we have the area and we need the x value. Inverse norm is the only one that will do that for us. And so we put in 0.09, comma 100, comma 15, and we would get the answer that way. Now let's check our work and see. And 15. Okay, so we got 79.888. 79.888. And they also said round to the nearest hundredth, so we'll put 89. That's pretty much all there is to it. Pretty straightforward. They're starting to get a little tricky. Look at this, the third quartile. And then they also define what the third quartile is. The third quartile is the 75th percentile. It is the top 25%. And they're also saying they've switched the mean to be 107 because we're talking about adults, I guess. And also the deviation is still 15. It says find the third quartile, Q3, which is the IQ score separating the top 25% from the others. So it turns out the third quartile is equal to the 75th percentile, which is also equal to, I think we saw that little notation. Top 25%. These are all saying the same thing. Pictorially, what would that look like? 75th percentile is about here. And we'll say that this all is 75%, which means this region, in fact, which means that region there is therefore 25%. And so what value, what function would I use to get x? Well, the answer is inverse norm. Inverse norm is pretty valuable. You got to put in the area to the left of the value you're trying to find to use inverse norm. And actually, we can't cut it off. For inverse norm, we're actually going to have to put in the mean, and we're going to have to put in the standard deviation as well. It was 1/5. I think it was like 115 or something like that. Let's see. Let's go back there. 107. Standard deviation 15. So let's just do this again now. $117.1. All right. Now, what we'll do, let's just scan the others, just make sure they're all nice and straight. These are very straightforward problems. These are really good problems. Convert these to inches and then you're home free. Find the percentage of women that meet the requirement. This is your lower bound, this is your upper bound, your mean, and your deviation. Same thing over and over again. They're giving you your lower bound, your upper bound, your mean, and your deviation. These are really good problems. Assume human body temperature is normally distributed with a mean of 98.28, 0.21 and standard deviation 0.63 degrees. A hospital uses 100.6 degrees as the lowest temperature considered to be a fever. What percentage of normal and healthy persons would be considered to have a fever? Does this percentage suggest that a cutoff of 100.6 is appropriate? Well, what we'll do is do our lower bound would be 100.6 and our upper bound would be, let's take a closer look at this problem. So for body temperature, 98.21 is the mean with a standard deviation of 0.63. And then they said 100 in the middle is 98.21. And what they're asking us is what is this proportion? And so what we do is say, well, this is our lower bound, and then our upper bound is some very large number. And we could use normal CDF there. We put in our lower bound, our upper bound, some very large number, and then put in the mean and the standard deviation. And that would give you the percentage of normal and healthy persons considered to have a fever. You just plug all those values in there and you would be good. Plug all those values in. Okay. What conditions would produce a negative z-score? A z-score for a negative area, a z-score corresponding to an area located entirely in the left side of the curve, an area in the top 10%, or a z-score corresponding to an area located entirely in the right of the curve. What would be to the left of the curve? Now there was, before we depart, there was some questions from section 6.2, the standard normal distribution. So let's take a quick look at those questions and see if we can help the students out on that. And the question was for number 3. It says a statistics professor plans classes so carefully that the lengths of her classes are uniformly distributed between 48 and 53. Find the probability that a given class period runs between 50.75 and 51.5. Alright, so it would be helpful to make a picture of what we're seeing here. So a uniform distribution we know will look like a rectangle. And we're going from 48 to 53. And we know that this area is exactly 1 because that's just one of the rules that we know. The area is 1. Well, what's the difference between 53 and 48? So if we were to subtract them, I want to know what would the height be? If the area is 1 and this is 2, that's 5. This length is 5. So therefore this height must be 1/5. Because 5 times a fifth gives you 1. So now the question is, well, what would be the probability between 50.75 and 51.5? All right. So we have a lower bound and upper bound. The height is still a fifth. So what you can do is subtract these still. All right. It's actually going to be the difference between this is 0.75. And then times a fifth. Now 5 does go into 75 15 times. And so I got 0.15. I won't worry too much about those. Quite frankly, those were just trying to let you realize that there are different types of distribution problems out there. Let's look at number 12. It says assume that thermometer readings are normally distributed with a mean of 0 and a standard deviation of 100, a standard deviation of 1. So it's standardized. A thermometer is randomly selected and tested. For the case below, draw a sketch and find the probability of the reading between negative 1.48 and 1.95. So it says between negative 1.48 and 1.95. It's this one. I was just wondering if there were more pictures. No, normally it's more than just 3. That looks like the best choice. And then how would we find the probability of this? Well, because it's standardized, the default of the mean is 0 and the deviation is 1, and we have the lower bound and upper bound, we can use normal CDF. And that's all we'd have to do for that. We can go second, distribute, number 2, and put in the lower bound, negative 1.48, and the upper bound is 1.95. And just hit enter. I didn't even have to put in the 0, 0, 1. I could have, but I didn't. They want me to round this off to 4 places. It's 90.49, and if you round it off that 9 one more, that puts it at 50. So let's look at 13. Find the probability that a given score is between negative 2.08 and 3.92. It looks like that one. And what would be the probability? Well, this time we're just going to put in our lower bound is negative 2. Our upper bound, my lower bound is negative 2, and my upper bound is 3.92. I'm hearing that the video is a little fuzzy. How's the quality? Okay. We may have to go back to Panopto. Maybe I have to update this software. Was this problem clear? Would you be able to get the area for the probability here? Can't I just do normal CDF of the lower bound and the upper bound at this point? Let's finish this problem off. Okay, and let's put in the lower bound, negative. I'm just going to delete I'll just write over it. And 3.92. I knew it would be a lot, right? 0.98, 112. Which graph represents the 85th percentile? So we said D, and what would be the temperature of the 85th percentile? Well, you have to use inverse normal 0.85. Let's go to the other question. There was another question about number 17. Find the indicated area under the curve of the standard normal distribution, then convert it to a percentage and fill in the blanks. About blank of percentage of the area is between -1 and 1. Well, that's going to be 68%. Now, how would we do this problem now? Just do normal CDF. Second, distribute normal CDF of -1, 1. And they want you to convert this into a percentage. So 68.27. And we got it done. Thanks for watching, guys. We're going to wrap it up here. We're going to do the next 2 sections on Tuesday, live and direct, live and in living color. We will see you soon. Have a great weekend. Still lots of weekend left. And make sure you understand this. Do the homework. Spend some time on this. These questions are extremely important in statistics, and this will help guide you to do more practical problems in statistics. Having a normal distribution is really important. Later on, we're going to see if we don't have a normal distribution, we'll know how to create one by taking sample sizes and the averages of the sample sizes. So it turns out the average of the averages is normally distributed, and then we will run some statistics on that. I'm glad this was helpful, and hey, have a nice day. Bye bye.